Okay. Now we prove the measurability criterion. So we start with the subset of X. We just denote by B the image of that. B1 will be the subset of B, which is a complete pre-image, and B0 will be the subset of B which is not a complete pre-image. We start with the assumption that A is measurable. By definition, for every epsilon, I can produce A dash from the minimal enveloping ring such that this external measure is less than epsilon. Now, I'll first claim the following embedding, that B0 is a subset in this image. Here it is. If Y in B0, then remember B0 is the collections in B, is a subset of B, which is not a complete pre-image. So there's an element in A such that Y is the value of F at the point X because of this. But on the other hand, because it's not a complete pre-image, there is another element which is not in A such that, again, Y will be the value of F at that point. Right. Now, this further implies that we need to consider two options. First, consider the simplest one when X is not in A dash, which means that X is in a symmetric difference like that, and that will conclude the proof, because that is enough to conclude that Y is in the right hand side. However, if X is in A dash, I claim that X0 will then be also in A dash. This is due to the fact that A dash is a complete pre-image. Look at this. A dash is the A dash, because it comes from the minimal enveloping ring, it has the following structure. It's the disjoint union of complete pre-images, so A dash by itself is also a complete pre-image, right? Which means in particular that if you have a point in A dash and you have some other point, not necessarily in A dash, such that it delivers the same value, this point is in fact should be in A dash. So because X0 delivers the same value as X under the mapping F, X0 must be in A dash if X is in A dash. And that's why in this, if you consider this possibility, then X0 will also be in A dash, which means that because X0 is not in A, X0 in the symmetric difference, and that means that Y is again in the right hand side, because F of X0 delivers the value, the point Y, maps into the point Y. That's why we do have this embedding, and that's why if you take the external measure of B0, that's less than the measure of, in fact, it's an asterisk missing here, I'll fix it in a sec, and that's less than epsilon. And observe this, the left hand side here is independent of epsilon. Epsilon is arbitrary positive number, you can push it to 0, and that will imply that actually the measure of G star measure of B0 is 0. Now, that's a half of the conclusion. So we start with the assumption that A is measurable. We concluded now that the B0 is the measure 0. We also have to conclude that B1 is measurable, and that's the argument for that. We explicitly construct the set B dash, which is the image of A dash, and that will be the complete image, because A dash is a complete pre-image. I claim the following embedding. I'm not going to argue this. The argument should be something like this, something similar. But if this embedding is true, then you can estimate the external measure of the left-hand side here is the sum of the external measure of this and of this. This is epsilon. This is just 0, which is established this, and we have the epsilon, which means that we look at this. For the set B1, we produced an element of the minimal enveloping ring, which approximates this element B1 in terms of the external measure. This is exactly the definition of measurability, the back measurability. I'd like to emphasize that actually the key point in the whole argument here is this relation between sets A, B1, B0, and A dash and B dash. Here they are. The f of x belongs to B dash if and only if x belongs to A dash. It's the reflection of the fact that A dash is a complete pre-image of B dash. On the other hand, f of x belongs to B1 implies that x belongs to A. That's the fact that B1 consists of complete pre-image points of the set A. That's the B1. And the fact that f of x belongs B necessarily follows from the fact x belongs to A. This is just a definition of B as the image of the set A. These three relations, in fact, justified everything here, justified this chain of implications, and thus this embedding, they also can be used to justify this embedding. Alright, now we prove the opposite implication. We start with the assumption that B0 and B1 are measurable, and with the extra assumption that the B0 is a measure 0. B0 and B1 are defined up there. Now our job is to show that the set A is Lebesgue measurable. So we fix an epsilon. Because B1 is measurable, we know that there is an element in minimal enveloping ring such that this one is less than epsilon. We explicitly set A dash to be this pre-image, and now we claim that we have this embedding between the sets we constructed. Again, this embedding, I'll show the details, but it is based on these relations I mentioned earlier. Look at this. I start with the element in the left-hand side. That's the left-hand side. This splits in two options. Either you have x in A and x not in A dash, or we have x not in A and we have x in A dash. Now, x in A dash, it is equivalent to f of x being in B dash, or x not in A dash is equivalent to f of x not being in B dash. And this condition, here I need to consider options. If x in A, then f of x in B, which means we have f of x either in B0 on B or B1. Remember, B0 and B1 together, they disjointly constitute B. Now, this part delivers the right-hand side immediately. Where is it? Here. So we have right-hand side right away from here. If we have this condition combined with this condition, it implies that f of x belongs to the symmetric difference of B1 and B dash, or x belongs to the pre-image of that. That finishes the analysis of this branch. Now, in this branch, again, when x in A dash, this is equivalent to f of x being in B dash. Now here, again, I'll consider options. First one, I'll consider f of x in B0, which delivers right-hand side, because of this part of the right-hand side. Now, the negative of that, f of x not in B0, implies that f of x must also be must not be in B1 also. To see that, we'll just assume the contrary. So assume that f of x in B1, which will imply that x in A, and that will be in contradiction with this piece. So if you have f of x not in B0, you also will have that f of x not in B1. Now this, combined with this assumption, again delivers this part of the right-hand side, and so we have the right-hand side again. Now we can finish the estimate. Because of this embedding, I can now say that the external measure of the left-hand side here is controlled by the sum of the external measures here, which is these two external measures. We know this is 0, and we know this is controlled by epsilon. So look, for the set A such that these two conditions are true, we found an element of A dash in the minimal ring, which approximates A in terms of the external measure. This is a definition of Lebesgue measurability.